Have you ever wondered if you could just zoom in, like all the way in, and watch a single chemical reaction happen? Or maybe pick out one specific molecule from a whole sea of billions? Well, today, we're going to dive into some absolutely revolutionary technology that's making that exact thing possible.
Okay, to get a handle on this, picture this. You're trying to study one particular dancer in the middle of a huge, packed, chaotic dance floor. How in the world would you isolate just their moves, their unique style? For decades, this was pretty much the exact problem chemists were up against, just, on a molecular scale.
For the longest time, the tools we had could only give us what's called an ensemble average. And that's basically the blurry, combined motion of billions and billions of molecules all doing their thing at once. We were seeing the overall vibe of the crowd, but we were totally missing all those amazing individual details.
And the difference here is, well, it's night and day. On one side, you've got the ensemble average. It's like the roar of the crowd. It's blurry, it's indistinct. But on the other side, the single molecule approach, that's like hearing a single whisper. You get this incredibly sharp, individual picture of what's really going on.
So there you have it. That's the core challenge, what scientists have dubbed the molecular crowd problem.
Now, scientists did have this fantastic tool called Raman spectroscopy. The way it works is, you shine a laser on a sample, and the way that light scatters back gives you a totally unique vibrational fingerprint for each type of molecule. It's an incredibly powerful way to figure out what's what.
But, and you knew there was a but, there's a huge catch. The Raman signal from just one molecule is unbelievably weak. It's like trying to hear that single whisper from a mile away. For a long, long time, this weakness just made seeing a single molecule completely impossible. The first major breakthrough, the first big crack in this problem, was a technique called SERS. That stands for Surface Enhanced Raman Spectroscopy. And let me tell you, this was the game changer that finally made those single molecules shine.
So how on earth does SERS work? Well, the secret is in these teeny tiny metal nanoparticles. Think gold or silver. When light hits one of these particles, as you can see down in the diagram, it makes the whole cloud of electrons around it start to vibrate like crazy. This collective wiggle is a phenomenon called a localized surface plasmon resonance.
So what that vibrating electron cloud does is it basically turns the nanoparticle into a tiny nanoscale antenna. And just like a radio antenna can boost a weak signal, this little guy massively amplifies the super faint Raman signal from any molecule that happens to be sitting right next to it.
And when I say massively, I am not kidding. The signal can get amplified by up to, wait for it, 10 billion times. This isn't just turning up the volume a little bit. This is like going from a whisper to a supersonic jet. I mean, what an incredible scientific leap.
But here's the thing. This incredible enhancement isn't just spread out everywhere. If you look at this calculation here, you can see that energy gets super concentrated into these tiny little areas called hotspots, especially right in the gap between two nanoparticles. That's the sweet spot. That is where the magic happens.
And just like that, boom, the impossible became possible. With this massive amplification from SERS hotspots, scientists could finally, for the first time, detect the unique vibrational fingerprint of one single molecule.
But of course, this amazing victory immediately brought up a new question. We knew these incredibly powerful hotspots existed, but how could we find them? They were the whole key to the thing, but where exactly were they?
And that was the problem with SERS. These hotspots, they just form in random locations where a couple of nanoparticles happen to bunch up together. You basically had to get lucky. So it's incredibly powerful, but also really imprecise. It's kind of like dropping a microphone randomly into a huge stadium and just hoping you pick up the right person's voice.
So this whole challenge of imprecision, this randomness, is what led to the next great innovation, TERS, or Tip-Enhanced Raman Spectroscopy. You can think of this as the ultimate zoom lens for the molecular world.
The idea behind TERS is just so elegant. You take that powerful signal-boosting hotspot, and you gain complete control over it. The question was, what if you could just stick it right on the very end of an atomically sharp needle?
And that's exactly what TERS does. This schematic shows you the whole setup. It combines a super powerful scanning probe microscope, which gives you unbelievable precision, with the chemical sniffing power of SERS. All of that enhancement gets focused right at that single movable tip.
So now, instead of just randomly searching for hotspots, scientists can move this tip with sub-nanometer precision.
They can decide exactly where they want to look and place that enhancement right over the molecule they're interested in. They're in complete control of the spotlight.
So what can we actually do with this incredible new power? This is where we finally get to spy on single molecules, right in the middle of the action.
This right here, this is where you really see the power of TERS. Look at this image. The top part is a topographic map. It shows us the physical shape, what the molecules on the surface look like. But that heat map on the bottom, that's the TERS data. That shows us what they're made of. We can actually tell the difference between two kinds of molecules just by scanning the tip over them. We're not just seeing shapes anymore, we are reading chemical labels.
This just opens up a whole new universe of possibilities. We're talking about watching a single chemical reaction as it happens, mapping the structure of DNA, molecule by molecule, designing electronics on the molecular scale, and finally understanding, at the most basic level, how things like catalysts and batteries actually work. It's just incredible.
And I want to be clear, this isn't just a small step forward for science, this is a huge leap into an entirely new frontier.
As the researchers put it themselves in their paper, these techniques provide new insights on molecular behavior that would otherwise be obscured. In other words, we're finally seeing the individual dancers, not just the blurry motion of the crowd.
So we can now see and identify the fundamental building blocks of our entire world with absolute, perfect clarity. The question this leaves us with is a big one. With this incredible new vision, what will we choose to build?